Here we discuss about the time harmonic fields. So we have seen on the live session that the time harmonic case, the source functions rho and j are harmonic in time, or they are sinusoidal functions. So since the Maxwell equations are linear differential equations, the corresponding fields E, D, B and H are also sinusoidal. They are also harmonic in time. So the advantage of using the harmonic function is that any arbitrary periodic function can be expanded as the superposition of sinusoidal functions having different frequencies using Fourier series method. So, if rho and j vary with a particular frequency and they are harmonic too, then corresponding fields E, D, B, H will be also sinusoidal and they vary with the same frequency as that of the source functions, since the Maxwell equations are linear differential equations. We know that the instantaneous expression of a sinusoidally varying quantity, for example current, can be written as I of t is equal to I into either cosine function or sine function. So if we choose cosine reference, we can write this as I cos omega t plus phi. I is the amplitude, omega is the angular frequency, which is equal to 2 pi f, and phi is the phase. So this is the instantaneous expressions. So but when there are equations which involve derivatives and integrals of psi, it is difficult to solve. കാരണം ഡെറിവേറ്റീവ് വരുമ്പം സൈൻ ഫംഗ്ഷൻ വരും, ഇന്റഗ്രൽ വരുമ്പോഴും സൈൻ ഫംഗ്ഷൻ വരും. അപ്പോൾ അത് സോൾവ് ചെയ്യാൻ ബുദ്ധിമുട്ടായിരിക്കും. സോ ഇൻ സച്ച് കേസസ്, ഫോർ എക്സാമ്പിൾ ഇൻ ദ കേസ് ഓഫ് LCS സർക്യൂട്ട്, നമ്മൾ ഓൾറെഡി ലൈവ് സെഷനിൽ ഡിസ്കസ് ചെയ്തതാണ്. സോ in the case of LCS circuit, it is very difficult to solve the current if you use the instantaneous expression like this. So in such cases, we use the phasor notation. So here I cos omega t plus phi can be written as I into the real part of e to the power j omega t plus phi. So I can be taken inside. So we know that cos omega t plus phi is the real part of this. E to the power j omega t plus phi is cos omega t plus phi plus j sin omega t plus phi. So I e to the power j phi can be written into e to the power j omega t. Here I in e to the power j phi is called the scalar phasor Is. So this can be written as real part of Is into e to the power j omega t, where Is is the scalar phasor that contains the amplitude and phase information, and that are independent of time. So since I is this equations containing derivative of I, di by dt can be written as real part of Is into j omega e to the power j omega t. And the integrals of I can be written as real part of Is e to the power j omega t divided by j omega. So it is easy to solve equations containing the derivatives and integrals of I. Since we can cancel the e to the power j omega t term as well as the real part term from the each and every term. So we have already discussed the example of LCS circuit in our live session. So once the phasor is known, the corresponding instantaneous expression can be found as I of t is equal to real part of Is into e to the power j omega t, where Is is the scalar phasor here. So in time harmonic electromagnetics, so time harmonic electromagnetic means the electromagnetic case where the source functions are sinusoidal functions. So therefore the field vectors are also sinusoidal functions of time. So the field is a vector, and therefore we use a term vector phasor there. So the field vectors, which are functions, sinusoidal functions of time, and they vary with the space coordinates x, y, z, can be represented with the help of a vector phasor that depend on space coordinates, but they are independent of time. So suppose our instantaneous expression is for electric field is E, x, y, z, t. So this can be written as real part of the corresponding phasor E, x, y, z, e to the power j omega t. So here E, x, y, z is the vector phasor that is independent of time. So this vector phasors has got the amplitude, direction and phase information, but they are independent of time. So they are in general, they are complex. Because J5 in the term phase and e to the power J5, they will be complex in nature. So since electric field is represented by the vector phasor, so this is the instantaneous expression, this is represented by the vector phasor Ex, Y, Z. Then the derivative dou E, X, Y, Z, comma, T with respect to T is represented as j omega. So wherever derivative occurs, we can replace it by j omega. J omega E, X, comma, Y, comma, Z. And wherever integral E of x, y, z, t with respect to t occurs, we can write it as E, x, y, z by j omega. So wherever higher order derivatives occurs, we can write it as in the powers of j omega, and wherever higher integrals occurs, we can write it as powers of 1 over j omega. So now we can write the time harmonic Maxwell equations for a simple medium. So simple medium means linear, homogeneous and isotropic medium. So before writing the time harmonic Maxwell equations, we can write the Maxwell equations in terms of E and H for a simple medium, and they are given by del dot E is equal to rho by epsilon, del dot H is equal to 0. We are going to write in terms of E and H. So since del dot B equal to 0, del dot H is also 0, and del cross E is equal to minus dou B by dou T. B can be written as minus mu dou H by dou T. So B is mu into H. So minus dou B by dou T is this. So del cross E is minus mu dou H by dou T. So phasor notation lella nammal instantaneous expression aayidunathu ee phasor notation like maattum. Then del cross H is equal to J plus, so since it is a linear, D can be written as epsilon E. So J plus epsilon dou E by dou T. So these are the Maxwell equations in terms of E and H for a simple medium. So now we are going to write the corresponding time harmonic Maxwell equations. So when the sources rho and J are harmonic in time, the corresponding fields E and H are also harmonic. So we can write this in phasor notation. So rho and J are source phasors, and E and H are the vector field phasors. So here we can write this as del dot E is equal to rho by epsilon, no change. Then del dot H is equal to 0, and del cross E is equal to So in phasor notation, wherever dou by dou t occurs, we can replace it by j omega. So minus j omega mu h del cross E is equal to minus j omega mu h, and del cross h is equal to j plus dou by dou t is replaced by j omega. So in phasor notation, wherever dou by dou t comes, it is replaced by j omega. J omega epsilon E. So these are the time harmonic Maxwell equations for a simple medium. So these are represented in terms of the source phasors rho and j, and the corresponding vector field phasors E and H. So here E and H are functions of x, y, z only. They are not functions of time since they are phasors. So in this equations, E, H and rho and j are phasors. So we have used the same notation for phasors as well as for the instantaneous time dependent quantities. So this will not create any confusion, because now onwards we exclusively dealing with the time harmonic fields and therefore with phasors. So suppose we want to distinguish an instantaneous quantity from a phasor, we will put the argument T in the bracket. So, ഇനി നമ്മൾ എഴുതുന്നത് മുഴുവൻ phasor notation ആയിരിക്കും. So, we use the same symbol for the phasor as well as the instantaneous expression. Subscript ഒന്നും കൊടുത്തിട്ടില്ല. Phasors are independent of time. So, quantities with an argument T inside it are generally instantaneous expressions, and we have to note that any quantity containing j should be a phasor. Now we can write the time harmonic wave equation for the scalar potential and the vector potential. So we know that the non-homogeneous wave equation for the vector potential is given by del square A minus mu epsilon dou square A by dou t square is equal to minus mu j. So in phasor notation or in the time harmonic case. So in time harmonic case we use the phasor notation. This is written as del square A minus mu epsilon. So wherever dou by dou t occurs, we replace it by j omega, and wherever dou square by dou t square occurs, we replace it by j omega whole square A is equal to minus mu j. So del square A, j square is minus 1, j is root of minus 1. So minus minus is plus, plus mu epsilon omega square A is equal to minus mu j. So this can be written as del square A plus k square A is equal to minus mu j, where k square is equal to mu epsilon omega square and k is equal to omega root mu epsilon. So root mu epsilon is 1 over the velocity of propagation. So k is equal to omega by u, 2 pi f by u. U is the velocity, which can be written as frequency multiplied by wavelength. So lambda into frequency gives u. So f will get cancelled, 2 pi by lambda, the wave number. So we have del square A plus k square A equal to minus mu j. So similarly, the non-homogeneous wave equation for scalar potential is given by del square V minus mu epsilon dou square V by dou t square is equal to by epsilon. So please get the corresponding time harmonic expression. So this is an assignment for you. So the corresponding time harmonic wave equation for vector potential is given by del square V plus K square V is equal to minus rho by epsilon. So where K is the wave number. These two equations, del square A plus K square A is equal to minus mu J, and del square V plus K square V is equal to minus rho by epsilon, are called the non-homogeneous Helmholtz equations. Non-homogeneous Helmholtz equations. So in the time harmonic case, the non-homogeneous wave equation for scalar and the vector potential reduces to the non-homogeneous Helmholtz equations. So here K is the wave number. And similarly, the Lorentz gauge condition del dot A plus mu epsilon dou V by dou T equal to 0 under time harmonic conditions is given by del dot A plus dou by dou T is written as j omega mu epsilon V equal to 0. So this is the Lorentz gauge condition in time harmonic case. Lorentz gauge condition in time harmonic case or in the phasor notation. Now we can get the expression for the retarded scalar and vector potential due to time harmonic sources. So we know that the retarded scalar potential is given by V of RT is equal to 1 by 4 pi epsilon integral rho T minus R by U divided by R d V prime. And AFRT, the retarded vector potential, is given by mu by 4 pi integral J of T minus R by U dV prime divided by R. These are the solutions of the non-homogeneous wave equation for scalar and vector potentials. അപ്പോൾ നമ്മൾ പറഞ്ഞു ടൈം ഹാർമോണിക് ഫീൽഡ്സ് കേസിൽ non-homogeneous wave equations reduces to non-homogeneous Helmholtz equations. So under time harmonic case we have to get the solution of the non-homogeneous Helmholtz equations. So time independent ആയിരിക്കും, അത് phasors ആയിരിക്കും അല്ലേ. അപ്പോൾ ആ phasors കണ്ടുപിടിക്കണം. The phasor solutions of the non-homogeneous Helmholtz equations have to be find out. So അത് നമ്മൾ എങ്ങനെ ചെയ്യുന്ന വെച്ചാൽ വി ഓഫ് ആർ ടി എന്ന് പറഞ്ഞാൽ നമുക്കറിയാം വി ഓഫ് ആർ ഇ ടു ദി പവർ ജെ ഒമേഗ ടി 1 by 4 pi epsilon integral rho of t minus r by u എന്ന് പറയുന്നത് നമുക്ക് റോ ഇ ടു ദി പവർ ജെ ഒമേഗ ടി ആയിരിക്കില്ല അതിന്റെ ആർഗ്യുമെന്റ് ടി മൈനസ് ആർ ബൈ യു. So phasor into this by r dv prime. So we get v of r e to the power j omega t is equal to 1 by 4 pi epsilon rho into e to the power j omega t e to the power minus j omega r by u divided by r dv prime. Omega by u is nothing but the wave number k. നമ്മൾ കണ്ടിട്ടുണ്ട് 2 pi f by f lambda, 2 pi by lambda k. So we have, so this integration is with respect to volume. So e to the power j omega t can be taken out and we can cancel it on both sides. We get v of r is equal to 1 over 4 pi epsilon integral. So e to the power j omega t നമ്മൾ പുറത്തെടുത്തു ക്യാൻസൽ ചെയ്തു. Rho e to the power minus j omega by use k j k r by r dv prime. So similarly we can get the value of a of r. A of r എന്ന് വരുമ്പോൾ എന്ത് ചേഞ്ച് വരുമെന്ന് നിങ്ങൾക്കറിയാം. Similarly you get the value of a of r. This is an assignment for you. So we can get a of r as mu divided by 4 pi integral j e to the power minus jkr by r dv prime. So these are the phasor solutions of the non-homogeneous Helmholtz equations. So these two are the solutions of the non-homogeneous wave equations. So similarly these two are the solutions of the non-homogeneous Helmholtz equations. So these are phasors too. These are independent of time. Or we can say that these are the expressions for retarded scalar and retarded vector potentials due to time harmonic sources. So here e to the power minus jkr is an exponential function. We know that any exponential function can be expanded using the Taylor series as. So e to the power x can be written as 1 plus x square by 2 factorial plus x cube by 3 factorial plus etc. Similarly, e to the power minus jkr can be written as 1 minus jkr plus minus jkr whole square by 2 factorial plus etc. So 1 minus jkr, j square is minus 1, minus square plus into minus k square r square by 2 factorial plus etc. Here k is the wave number, which is 2 pi by lambda. So k into r is 2 pi by lambda into r. So if the frequency with which rho and j changes and therefore the field changes is very small, then the corresponding wavelength is very high. Then r by lambda, r is the range and lambda is the wavelength, is very small. Lambda is very high, r is very small. So r by lambda is very small. So k into r, 2 pi by lambda, r is also very much less than 1. So e to the power minus jkr can be approximated as 1 if this kr is very much less than 1, since the distance r is very small compared to the wavelength lambda. So this is very small, and here Iroda powers are very small. So we can neglect the terms, and e to the power minus jkr can be approximated as 1. Then the expression for v of r and a of r will become, when e to the power minus jkr is 1, v of r is equal to 1 by 4 pi epsilon integral rho dv by r, and a of r is equal to mu by 4 pi integral j dv by r. So these are the solutions of the corresponding Poisson equations. So when r is very much less than lambda, r by lambda is very much less than 1. So in that case we can do this approximation, and these are nothing but the quasi-static approximations. So if the frequency is very small, then the wavelength is very large, and the solution of the non-homogeneous wave equation reduces to the solutions of the Poisson equations, which are the static equations. So this is called the quasi-static approximation. So this is true only for very small frequencies. So if the frequency is very high, we have to use these expressions to find the phasor corresponding to the scalar potential and the vector potentials. So these expressions are the general expressions. We can use these expressions for both the low frequencies and high frequencies. For low frequencies, this expressions reduces to the corresponding quasi-static solutions. So now we can check the procedure for determining the electric and magnetic fields due to time harmonic sources. So time harmonic sources means time harmonic charge and current distributions. So rho is harmonic in time and J is also harmonic in time. That means rho and J are sinusoidal. So for that, in order to get the fields, what we have to do is that we have to find the phasors V of R and A of R using these expressions. So first of all, we have to find the phasors V of R and A of R from the equations 1 and 2. Then we have to find the corresponding field phasors E of R. So we know that E is equal to minus del V minus dou A by dou T. So in phasor notation it is E of R is equal to minus del V minus j omega A. Dou by dou T is replaced by A. And B of R is equal to del cross A itself. So these are the field phasors. So when the phasors are known, the corresponding instantaneous expression, so that is the third step, the instantaneous expression for the fields can be found as E of R t is equal to real part of E into E of R into e to the power j omega t. And B of R t is equal to a real part of B of R into e to the power j omega t for cosine reference. These are the instantaneous expressions for electric and magnetic fields. So this is how we find the instantaneous fields. So if you're using a sine reference, we have to take an imaginary part instead. So this is the procedure that we follow for the time harmonic problem, where the source functions are harmonic functions or sinusoidal functions, so that the corresponding fields are also harmonic or sinusoidal. Okay, thank you.